We have three speakers in a row in this session, and the first speaker will be given remote by video. It is a talk by Professor Dierk Raabe. Dierk Raabe is actually Chief Executive of Max Planck Institute for Iron Research at Düsseldorf in Germany, and professor at RWTH Aachen. He is one of the most versatile, brilliant scientists in the field of metallurgy, a totally counter-example of what many people consider an old-fashioned topic. Dirk, would you please start your talk? Here he is, yeah.
Yes, good morning. Thank you very much. I think it was you, Wilfried, for the nice introduction. And I hope everybody can see and hear me okay.
Yes.
Otherwise, please let me know.
It's okay.
Great. Good. So I hope you also see the first slide in the projection mode. So I assume you see the first slide okay, and it's a big pleasure to be on board today, and thank you very much for having me. And the talk will be about some material science aspects associated with green steel making by using hydrogen-based reduction methods. And the work is essentially led by two very fine young colleagues, Ismail Filho Souza and Jan Ma, and you see both of their faces here. They are group leaders in the Max Planck Institute and are the brains behind many of the things that we are presenting. But I will highlight the contributions of the other colleagues, of course, as we go along. I am very thankful for funding that we receive from several sources about this type of work. And we all know that in the area of steel, you must think big, particularly if you want to change or revolutionize some of the ways how we make steels. And the forecast for 2050, as an example, projects the incredible amount of 2.8 billion tons of steel, give and take. And what we see here in the bottom row is essentially the net version of the total redox equation, through which about 70% of the steel is nowadays produced from the 2 billion steels that we produce around on the globe, going through the blast furnace and converter route, as you all know, and essentially consists in pumping hot oxygen into a fossil carbon carrier like coke, and that produces carbon dioxide. The carbon dioxide goes through the boudoir reaction, producing carbon monoxide, and carbon monoxide is the main fossil reductant to start reducing the hematite. And that is, in the global average, I must say, currently translating to about 2 tons of CO2 produced per 1 ton of iron. So that's the setting in which we are thrown. And that explains where the huge industrial greenhouse gas emissions in this sector come from. So when we take a step back and look, what kind of scientific options do we at all have at our disposal to rethink that gigantic and long-grown system, then we have, of course, a variety of feedstock materials at our disposal. You see here as an example the lump ores, pellets. That's kind of the standard iron ore material that you would currently feed into MIDREX, direct reduction, or blast furnace reactors. Fines, the lowest price variant, is very interesting, which is sintered into the pellets, which in itself is a very CO2 intense process. But we also have, of course, different waste feedstock materials at our disposal from industry, already dumped waste, even think about red mud, things coming from the bauxite refinement, and of course organic waste and scrap and so on. On the reductant side, we have, of course, hydrogen as one of the possible options in the future in consideration, but also corresponding vectors, be it ammonia and methane, and I come back to some of these other hydrogen-carrying reductant molecules that might be worth consideration. And then you can bring these different feedstock types, of course, in different pathways and in different reaction principles together. Now that would translate to certain type of reactor concepts. Some being close to what we already have, others maybe being under consideration for redesign. Blast furnace use of some of these feedstock types, as I mentioned, is of course limited because you need that percolation through that rigid feedstock of the coke and the pellets and so on. Electrolysis is quite interesting, yet I do not discuss that today at all. And then we have the classical, long-known MIDREX direct reduction ovens that run on methane typically, and also very interesting variants on the fluidized bed side, so where fines instead of pellets are used. And then we have the electric arc furnace and many, say, electrically fueled furnaces that might be deserving a second look in that context. And whatever we do, we will have to understand that there's a certain trade-off due to the huge quantities that I have mentioned between the use of electricity and the use of, say, buffer chemicals, be it hydrogen or ammonia, that we have to produce by sustainable energy. Otherwise, it's not helping much. And that means whatever we do, we must keep on the screen for the corresponding life cycle evaluation, where that corresponding electrical energy is coming from, that we use either for the electrically driven processes, being electric arc, plasma operations, or the fuel electrolysis cells, or for the production of the hydrogen ammonia. That means we must always consider the carbon dioxide footprint, of course, of the associated energy sources. Otherwise, we don't really gain much. So I will talk in this presentation about three variants, namely reduction of iron oxide by hydrogen, by electrons, and plasma. And I start with the well-known textbook example of direct reduction, which you have around the globe already in different flavors, essentially a static shaft bed reactor, where the word static is not quite correct because under the swelling and shrinkage and change and abrasion, you have quite a lot of mechanics and dynamics in these ovens. But in principle, they currently operate under methane or different syngas mixtures, which in part already contain hydrogen. And then you create a material that is porous iron, is referred to as iron sponge, that is then downstream fed, for instance, into an electric arc furnace, as is sketched here. And that has a very high potential for massive carbon dioxide reduction, and many companies around the globe are currently purchasing such instruments and try to adopt them for different gas mixtures that you can later also swap between methane and syngas and hydrogen and so on. So I take now a couple of examples here. This is the reduction kinetics in a static reduction hematite experiment. This is a commercial pellet. I later show you more details about it at 700 degrees centigrade under pure hydrogen exposure. And what you see here is when you look at the right-hand side, where you see the reduction rate as a function of the reduction degree, then you can appreciate the very fast transformation from a trigonal hematite, the Fe2O3, into the cubic inverse spinel. And then the much slower further reduction to the likewise cubic wüstite and to the cubic body center cubic iron, because we are at 700 degrees centigrade, which is for an industry example rather cold, but we want to have these reactions not proceeding too fast. So you see you nearly lose an order of magnitude in reduction speed between the beginning and the end. And again, we keep in mind in iron, you must think big, and things that are slow are not good in iron making. So here's an example of an environmental microscopy experiment that was done by my friend, Professor Mark Willinger at ETH. He is now at the university in Munich. And he had a wüstite single crystal that we prepared, operated under hydrogen atmosphere and SEM. And what you can nicely see, if I let this movie run, I hope you can see it, that you can see how under this hydrogen atmosphere in the electron microscope, let me go back, how this is overgrown by dense and closely packed iron film, of course, because it's a surface-driven reaction. Now I go to a second ongoing experiment that is currently done at 500 degrees centigrade. That means we directly start here from magnetite, from the magnetite single crystal, and you are then at a temperature in the phase diagram below the wüstite phase. That means you directly transform magnetite into iron. And that is done now in a transmission microscope, in a Hitachi instrument, again under hydrogen. And let me run this movie. I hope you can see it okay. And please be aware, note here where maybe you see the pointer. I stopped the movie here, and I hope you can see it. You see maybe this bright appearing little sphere, this little bullet type of feature here in this otherwise, free volume area. And the free volume is a part of that transformation. It's thermodynamically very, very interesting because you cannot undergo these transformations without losing volume. That's the point of it. So we are here, so to say, in a grand canonical setting and not in a canonical setting. And that means when I let this movie run further a little bit, then you can see that this is the first iron nucleus that is growing inside of this free volume, because where the volume is opening up, that means you lost, of course, most of the oxygen through the surface that produces the water, and that's where the iron can be formed. So these are things that we just started to study really at a local scale in the electron microscope. When I now jump back to a polycrystalline material, that is a commercial hematite pellet, and I zoom a little bit in, now you cut that open, and you are at a late stage of, after 30 minutes, at 700 degrees centigrade under pure hydrogen exposure in a direct reduction setting. These are experiments by Jan Ma and Hauke. And you see then when we grow yet a little bit bigger that you have on the inside this gray appearing FeO, the wüstite, which is a cubic material. And you see then again this film that you could see in the microscope just before densely surrounding this Swiss cheese of the wüstite. Again, you have the oxygen vacancies collapse and form nanopores. The nanopores grow into micropores and so on. So I come back to those. So the elementary steps for this last sluggish stage of the wüstite to iron transformation are shown here. Left-hand side, the wüstite. Right-hand side, you see the iron layer. And the first reduction was, of course, at the surface, where water was formed due to the surface reduction of the wüstite by the incoming hydrogen, which must dissociate and react with the oxygen. Now, once you have formed the iron layer, you form a chemical potential gradient between that surface and the inner interface between wüstite and iron layer, so that the iron oxide the oxygen ion must leave behind 2 electrons, reducing locally the iron. Then this oxygen atom diffuses outbound following the chemical potential gradient to the next nearest surface. Doesn't have to be a free surface, very important. And the iron is reduced, relaxing on the inside so that the iron layer grows towards the inside. So that's the elementary ionic transport conditions here. When we look in the EBSD, you can follow this hematite pellet structure. You see it's a sintered polycrystal with a lot of inherited porosity, around 20%, 15 to 20% from the pelletizing process. And then the first reduction after 1 minute at 700 degrees, you see something like I would say, classical Avami type of surface nucleation plus growth. It's incoherent interfaces between the magnetite, mainly incoherent between the magnetite and the hematite. So there's not much surprise here. I mean, there are relevant details. But what is really interesting when you look into the transformation from the spinel into the cubic wüstite, then you see a very interesting type of gradual decomposition where the iron seems to be reshuffling on the remaining cubic lattice. And it's also, by the way, in the EBSD not so easy to measure because both are cubic structures. It's quite complicated actually to measure. And this is something I'm currently very interested in, the nature of this funny type of phase transformation. And of course, always associated with an ongoing further massive loss of mass, namely of the oxygen, which is then creating, of course, nanoporosity. And then the last stage is this very sluggish one from the wüstite into the alpha iron, as you can see here. Always with still encapsulated and closed and maintained wüstite in the center. So you have always gradients in the material. When we jump but a little bit deeper into the microstructure, you can see that not everywhere we have scenarios where the wüstite, like here in gray appearing, is completely surrounded by the bright appearing ferrite, but you have delamination and you have fracture, maybe here, maybe even supported by hydrogen, I don't know. But you have also an opening up due to the massive volume changes of free new volume, which is very important to understand finally the kinetics of these processes. You also build up G and Ds like you see in the channeling contrast here and so on. So it's very rich in microstructure, and which is in part due not just to the mass loss, which is thermodynamic, but also due to the huge stresses between the adjacent phases. We went deeper into the analysis of the porosity. This is just one example where you can see a set of pores, and those were closed pores. Now they have been illuminated here by local diffraction experiments in the stem so that you can see the phase contrast. You see here the red contrast showing where the material was fully reduced into body center cubic iron. All good and fine. But then you can see the pores in the center, which contained so much water building up so high pressure, as you can calculate with the phase field model or analytically, that you obtained local reoxidation. That means the volume around that pore, due to the captured water which could not escape, which could not percolate outbound, you have reoxidation of this inner perimeter around the pore. That's very interesting. And again, when you could say, okay, that's whatever, a second, third order effect, but it's not. Again, when you calculate the volume that is reoxidized simply because the water cannot escape, then you have a huge fraction that can in principle remain unmetallized. So in principle, we want to measure the water directly, and measuring water, as you all know, is at atomic scale very, very complicated. And so we have now worked since more than a year on an experiment that was mainly governed by Ayman El-Zoka. He is now at Imperial College and was with us as a Max Planck Institute, and Seho Kim, who is now professor in Korea, and Lee Stevenson back in Sydney, and Bet Gold. And we did the following experiment. We took a single crystal of wüstite, and we exposed that wüstite under cryogenic and UHV transport conditions to a hydrogen-reducing atmosphere for about a second. Now we had to test that out. And what happens then, let me move to the little movie. I hope you can see it. You can see these pink-colored atoms. This is the pure reduced iron, measured now at atomic scale. Then you see in the center of that sandwich the remaining wüstite layer, so the unreduced material. And you can see on the rims of this sandwich, so to say, colored here in yellow, the water content. And that is something which we try to understand and image by cryogenic atom probe tomography. This is the evolution of the porosity as a function of the reduction time, again at 700. So you see, you start with the inherited porosity from the sintering, and you end up with something like 45 to up to nearly 50% porosity, depending on pellet type, during the reduction. And that is, as I mentioned before, associated with the mass loss, and we'd also do corresponding tomography on that in order to better understand the trade-off between the inherited sintering and the percolation porosity. So we measure this also here in Stefan Zeffra's laboratory, where we have an automated 3D EBSD system, where, as you see in that little movie here, the robotic arm can do the entire serial sectioning by himself. So that is now not by a FIP, but this is by mechanical polishing. Then the robot puts the sample back in the electron microscope, runs the analysis, the EBSD analysis, and puts the sample back into the serial sectioning, into the polishing. And by that you get the distribution of these pores and can label them, classify them to pertain to the open or to the closed pores for the reasons I've mentioned above, because the outbound transport of the water will in future for an optimal metallization in such reactors be a very important point. Just another little clue towards the analysis of the purity effects, because we know that what you currently buy for such reduction processes are very pure iron oxides, but the future will be also, at least in some regions of the world, be about the use of much less pure iron oxide. That means we must also understand how can we design the reactors and operate them to cope with low purity, low price ores. Here's an example where we study, for instance, the silicon effect or even titanium effect and so on, producing, of course, oxides that are hard or impossible to reduce in such reactors. Another point is the boundary condition treatment. Here you see a commercial pellet, a little bit bigger than a centimeter in diameter. So I mentioned already, you can cut it open. You see the rich polycrystalline microstructure, the inherited porosity, and so on, similar as to what I've shown you before. You can make the phase contrast analysis But then we cast all of this into a corresponding Ginzburg-Landau calculation, so in a phase field model where we solve on the one hand the Cahn-Hilliard equation for the transport. We have the corresponding chemical reactions implemented to produce the water, and of course an Allen-Kahn theory that tracks the progress of the phase transformation. Here you can see how the iron is growing. Let me run this once again. And this is fully mechanically coupled, so you can see the full details in the ACTA paper. So we started off just by having a very simple elastic approximation where you reduce the lattice parameter by removing the oxygen gradually from the corresponding lattice, translating this into a Hooke strain. This adds to the elastic potential of the Landau functional. But we have now also added an elastic plastic formulation in a J2. That means isotropic form in the beginning, where at some high stress level, the stress is of course kept and you produce plastic deformation. So the details are in the paper, just for letting you know that I think it's also interesting for such complicated microstructure to start with proper boundary condition treatment. Now, another little sidestep that I mentioned on this overview diagram in the beginning, that it might be in the future be interesting to not just put all your money in such processes on the use of hydrogen alone, because the hydrogen is, so to say, the champagne of this industry. And when there's hydrogen production ramping up, I would doubt that most of this will be sold directly to the metallurgical sector, but it's likely to end up in fuel cell consumption, where we need very, very pure hydrogen. While in the metallurgical production, you can cope, or it would be actually good to have very low purity hydrogen. So hydrogen is not hydrogen, but you must really consider what kind of hydrogen do you use. And it could therefore be interesting to also blend ammonia in, which is a 180 million ton traded chemical. And so we did that. We used ammonia for direct reduction, and it works. The paper is now finally accepted in press end of the month. And so what happens is you have first an ammonia splitting into hydrogen and nitrogen. That is typically happening around 420 degrees in equilibrium, but due to the iron acting as a catalyst for ammonia splitting, that is well known, you produce it already at 350 degrees centigrade out of the waste heat. Then you produce a fraction iron nitride, as you see here, and alpha iron, and you produce, so to say, an iron nitride sponge. You charge that into an electric arc furnace, you melt it, and due to the vapor pressure, the nitrogen goes out and you have pure iron. That means you can make pure iron with green ammonia also. And we work, as I said, on other vectors too. Now, at the end, a few quick slides on plasma reduction. So you see in this overview picture that we also take...
Dirk, we have 3 minutes left, please.
Yeah, thank you.
For your talk.
Yeah, thank you very much, Wilfried. So the idea of plasma-based reduction is that balance between the consumption of hydrogen and the consumption of electrical energy. Because I said before, you must always balance your resources and to be flexible. So that can be done in existing electric arc furnaces that you all know for scrap remelting. And the idea is to equip them with a moderately reducing atmosphere. Here you see argon and hydrogen. We take only 10% hydrogen and even do experiments with even less. In the thermodynamic analysis here in the Ellingham diagram, you can of course appreciate when you produce a plasma according to ionization energies, you go through the SAR distribution, get the occupation of the different radicals, and then you have a much higher free energy. That means some of the reductant energy does not come from the molecule, but comes then from the ionization. What is interesting that such equilibrium calculations are of course a little bit short-sighted, because here's a very nice OS spectroscopy done by colleagues in Finland on our reactor, where you see the color code shows you the poisoning of the plasma by the evaporating iron. That means, in other words, when you want to do proper plasma theory, you must really do non-equilibrium theory, which is not trivial. Then we interrupt these types of experiments, as you see here, take out the samples and analyze them step by step by using classical microstructure analysis. So here are the interrupted experiments that you see, and you see due to the weight, the iron sinks readily to the bottom. After 10 minutes, 15 minutes, you have pure iron in your hand, and after 30 minutes, everything is done. That means it's also a very fast type of reduction method. So we do then all the details of the microstructure analysis. Maybe I won't bother too long with it. Maybe I would like to highlight just one interesting aspect that is shown here in the atom probe analysis. When you look on the left-hand side where you have the pure iron, this is an atomic scale frozen in partially plasma-reduced iron, and you see the wüstite left and the alpha iron right, and you see that the silicon is partitioning into the wüstite. And again, that's very important for the future when you want to use low price, for instance, banded silicon-containing iron ores. A second little detail is that you also remove the copper in the plasma. That is a very complicated thermodynamic step, which we have not fully understood yet. Just it's interesting in the electrification that we all know you get massive amounts of copper and tin and zinc into steels that are not so easy to come by. And when as a side product we get this removed, that would be very positive. Maybe this aspect I can just jump over. It's not principally different, but I jump right to the end. So this is my last slide, the overview slide, just showing you in a summary that I think we have a very interesting area or playground for advanced physical metallurgy before us, with all kinds of phase transformation and a lot of theory and experiments at our fingertips, with a huge leverage, of course, to make that community a little bit more sustainable. Thank you very much for your kind attention.
Thank you. Can we use the microphones? Yeah. Do you hear me, Dierk?
Yeah.
Yeah. Okay. So the talk is open to questions. Just a question about how close are you to some real process which would be viable economically?
Yeah, so we in our laboratory do not do too much upscaling ourselves. We really aim at doing the basic mechanisms, which I think are in this area not really properly done or understood. We have some labs, one big lab in Austria and another one in Berlin, who have both on the plasma and on the direct reduction side bigger reactors where you can do some upscaling experiment. And I think the biggest effect that needs close consideration is the so-called slag foaming, so the slag metallurgy, because many things, particularly element impurity removal, are done in the equilibrium between the liquid phase or the solid sponge phase, the slag, and the gas phase, particularly when it comes to the removal of the water of impurities from the reduced product. So we do collaborations, but we do not do everything in our own lab. We really focus on the basic science. Yeah.
Okay. Some other question? Yeah. John?
Yeah, Derek, very, very nice. This is John Parapesco.
Hi.
I was wondering this, in trained water in the reduced material, that's then carried forward for remelting into pig iron, I guess, or whatever. How does that affect the process downstream? Because this water could be kind of dangerous, especially if it's superheated and under high pressure.
Yeah, so thank you, John, for the question. So the amount of water, and indeed it's highly pressurized in these pores according to the calculations, is in the downstream melting. So you subject that typically together with scrap into an electric arc furnace. So that is a strategy you pursue. And there the total amount of water is so small that you don't have to expect, that the process is dangerous. So I know that myself as a student, I spent so many shift hours on these electric arc furnaces, 120 tons, that what is really dangerous, like in scrap cooling of a classical converter, what's really dangerous is if you have a gas bottle or a complete, a big amount of oil or so in the cooling scrap or in that scrap, but this amount of water is harmless. The main point why we think it's interesting, and it surprised us that we find so much water inside, is that simply you reduce the total amount of reduced material. And again, 2, 3, or 4% of unreduced material are in the steel industry a lot. When you multiply that by 70% being replaced in the future by direct reduction of the current blast furnace, multiplied by 2 billion tons of steel, and so then you talk big numbers. So it's not so much that the downstream is dangerous, it's much more that the metallization is insufficient.
Thank you.
Okay, thank you very much. I think we stop here. Thank you, Dierk, for this interesting talk. And bye-bye.
Bye-bye.